I would like to show you a work developed by Professor Maria Antonietta Aiello and Professor Sultan Ombres, which concern an open issue about the structural performance of concrete beams reinforced with FRP rebar. So this is the outline of the presentation. I will start with a brief introduction about the use of FRP rebar in civil engineering application. Then I'll show you some of the experimental tests and the results that were obtained. After that, we will see some of the numerical approaches developed by the author. And finally, we will discuss about some open issue regarding this topic. And I will conclude with some concluding remarks. So, as you may know, FRP rebar are being increasingly used for several civil engineering applications. And this is mainly due to the advantages that this composite material offer over traditional one. For instance, the high strength, the high corrosion resistance, the fact that they are not heat conductor, the invisibility to magnetic field, lightness, and finally, fast and easy application. Well, although these advantages, there are still some concern which are hindering the widespread use of FRP rebar in several civil engineering applications. One of them concerns their serviceability behavior with particular attention on both deformability and cracking evolution. In fact, well, it is well known that usually structure reinforced with FRP rebar are more deformable than similar structure with steel rebar. In addition, the linear elastic behavior of the FRP rebar may not guarantee adequate ductility requirement for the structure. And finally, another key aspect that must be evaluated in detail is the bond between the FRP rebar and the concrete. Because this is a crucial factor since it varies as a function of several parameters, both geometrical and mechanical. So, to try to comply with the current, with this current issue, the main objective of the present work was to provide a better understanding about the deformability and ductility of concrete elements reinforced with FRP rebar. To achieve this objective, the author performed some experimental tests, which were then coupled with some analytical studies, with particular attention to both deflection and cracking phenomena. So, as mentioned earlier, the analytical prediction, both the one proposed by the author and the prediction developed by current design code, for instance, the ACI, the Eurocode, or the Japanese code, were then compared with the experimental results. So, moving to the experimental investigation, in this study, 5 beams were tested under a 4-point bending configuration. Here, you can see the beam configuration in terms of internal reinforcement. So, in the bottom side of the beam, 2 CFRP rebar were positioned, while while 2 steel rebar were positioned on the top side. Then, regarding the beam geometry, basically, it was a 3-meter long beam, which presented a cross-section of 25 centimeters of width and 15 centimeters of height. And finally, regarding the steel stirrups, it basically employed the use of 2 8-diameter steel stirrups, which were spaced in 2 configurations. So, under the loading point and at the support, we can see that they were spaced the spacing was equal to 50 millimeters, whereas between the loading point and the support, the spacing was almost 100 millimeters. Then, well, regarding the material, the experimental campaign started with some material characterization tests. In particular, compressive and tensile strength of the concrete were equal to respectively 30.6 megapascal and 2.86 megapascal. Regarding the steel rebar, the average yield strength was equal to 142 megapascal. And finally, well, moving to the CFRP rebar, which had a diameter of approximately 8.8 millimeter, and was grain covered and helically wounded with carbon fibers. Basically, this composite rebar had a tensile strength equal to 2,400 megapascal, elastic modulus close to 130 gigapascal, and the ultimate tensile strain was equal to 1.87%. Finally, in this slide, you can see the main parameter that was varied among the experimental campaign, which basically consists in the number of FRP rebar, which varied from 2 up to 7. Here, well, you can see the setup, which, as I mentioned in the previous slide, it was performed under a 4-point, the flexural tests were performed under a 4-point bending configuration, and tests were performed until failure, using a load rate of 40 Newton per second. In terms of instrumentation, basically, you can see that the vertical deflection were measured by means of LVDTs, which were positioned under the loading point and at the midspan section, whereas the tensile strain of the CFRP rebar, as well as the compressive strain of the compressed concrete, was measured by means of electrical strain gauges. It is also worth mentioning that the crack width were monitored using some graduate magnifying lens. So, moving to the experimental results, in general, and starting with the failure mode, in general, all the beam presented the typical flexural failure, in which basically we could observe the crushing of the compressed concrete, as you can see in figure A. However, an unexpected result was observed for one beam, CB71, in which basically a shear failure occurred, followed by the concrete crushing at the loading point. This different failure mode could be mainly explained by the high reinforcement ratio, as can be observed. Well, CB77 represents the number of the CFRP rebar employed. And then from this spot we could already do some conclusion. For instance, with increasing the reinforcement ratio, it seems that there is an overall increasing trend of the ultimate load, whereas, well, this effect is more limited in what concerns the cracking load. Then, moving to the load displacement curve, in general, all the curve exhibited the typical bilinear behavior, which is typical for FRP reinforced concrete beams. In general, it is also, well, if you see this picture here, which is basically a zoom of here, it can be seen that increasing the reinforcement ratio led to an increase of the stiffness of the beams, but at the same time, we can observe a reduction of the ultimate deflection. Then, going to the moment curvature diagram, in general, similarly to what observed for the load deflection curve, the moment curvature diagram show a reduction in deformability as the reinforcement ratio increases. Another interesting observation then can be done in what concerns the crack width and crack spacing. In fact, well, as expected, and it is also typical for steel reinforced concrete beams, with increasing the reinforcement ratio, there is an overall reduction of the crack width. So, for instance, if we consider this curve, so the blue circle, which represents the beam with 7 CFRP rebar, and the orange square, which represents the beam with the 2 CFRP rebar, for instance, for 30 kilonewton, we can see that the crack width in the former beam was 0.40 millimeter, whereas a significant increase was observed for the beam with a low reinforcement ratio. In fact, basically, the crack width approached almost 1.80 millimeters, so much, much higher. Then, the experimental results were also used to some calibration of some analytical approach. In general, basically, the proposed model aimed to evaluate the stress and strain in the beam for each cracking configuration. The analysis, both at the serviceability and the ultimate limit condition, was developed by a nonlinear procedure. And basically, the model, the block model, was derived by a cracking analysis of a beam which is subjected to a bending moment higher than the first cracking one, and located between two flexural cracks which are supposed to be vertical. The analysis referred to the stabilized crack formation phase. In this situation, basically, the crack spacing varies between LB and 2LB, with LB being the development length. It is also worth mentioning that basically two limiting cracking configurations were considered in the analysis. The first one represents the maximum crack spacing, in which basically Lmax is equal to 2B. In this scenario, we have that basically the slip at the half point between the two cracks is 0, while the tensile stress in the concrete reached its tensile strength. On the other hand, regarding the minimum crack spacing, well, in this case, we can see that the slip at the half point between the two cracks is still 0, but the tensile strength, the tensile stress in the concrete is unknown, but lower than the tensile strength of the concrete. Well, here we can see the question that govern the static problem. So we have the axial equilibrium of the FRP rebar, in which we can see the area of the rebar, the perimeter of the rebar, the tensile stress, the bond stress. Here then we have the compatibility condition, and finally the equilibrium condition of the cross-section, in which this omega c represents the area of the cross-section. Basically, this numerical procedure can be solved only by some numerical procedure, which in this case, the author developed a procedure based on finite difference method. In this method, basically the block was divided in an element with small length delta, and basically the numerical procedure starts evaluating the stress and the strain at the halfway point of the cross-section by equilibrium equation, and imposing for symmetry the condition that the slip is 0. Therefore, it is possible to evaluate the stress and strain distribution at the edge cross-section of the first element contiguous to the halfway point. Then this procedure is extended to every contiguous element of the section, and it halts when the concrete tensile strain becomes 0, because at this point, basically, we have that there is the formation of the crack. The nonlinear bond slip law that was used in this numerical procedure was this one, that described the pre-peak and the post-peak. And in general, well, it is important to mention that the shape parameter, for instance, this alpha, S1, tau 1, S1 here, they must be calibrated based on experimental results. So, we cannot say that they can be completely generalized, but well, these highlight the importance of performing experimental results regarding the topic. Then the analytical results were compared with the experimental data, either both presented by the author and those provided by the current design code. In general, regarding, for instance, the ultimate load, we can see that the prediction, so here we have the experimental results, the prediction using the nonlinear model, and the ACI model prediction. In general, the ratio between nonlinear model and experimental results are quite good, being slightly underestimated with the nonlinear model, which provides slightly underestimated value, whereas the ACI model is a slightly the ACI model provides slightly overestimated results. But however, well, the estimates are very good. Then moving to the moment curvature curves, here basically the author analyzed the results that were provided using a sectional analysis. Then VM1 and VM2 basically represents the results from the nonlinear model, assuming two limiting cracking configuration, so both the minimum and maximum crack spacing. And then we have the results provided using the ACI model and the Japanese one. It is worth mentioning that the results provided by the model are based on the use of an effective moment of inertia of the cross-section. In general, as you can see from this slide, the results of the nonlinear model present a relatively good agreement with the experimental one, especially for the low value of the applied load. On the other hand, both the code models and the sectional one overestimates the experimental value in terms of moment curvature curve. Then, in terms of applied load deflection, here it can be seen that the nonlinear model proposed by the author are able to predict with good accuracy the experimental results, while on the other hand, similarly to what observed for the moment curvature curve, both the model provided by the code and the one obtained using the sectional analysis provides sort of overestimation of the experimental result, especially for the high value of the applied load. Then, regarding the crack width, here basically the author evaluated also the formula provided by the Eurocode. And basically, some of the observations that can be done are that, for instance, well, the Eurocode model provides consistently an underestimation of the experimental results. The results provided by the nonlinear model, well, I would say that they sort of overestimate the experimental results, while the ACI model presents good agreement with what observed experimentally. So, although the contribution of the present work, well, there are still several issues that must be further analyzed. In general, the experimental results shed the light on the fact that in terms of strength, the use of FRP rebar give a significant contribution. However, well, some concerns are still there regarding the high deformability which is observed under service condition. In general, well, the high deformability is mainly associated with reduced beam stiffness, which basically is a result of the diffuse cracking as well as high value of the crack width. Some of the solution that the author suggests to try to overcome this issue can be, for instance, associated with the use of FRP rebar with different surface finish configuration, which may improve the mechanical interlock between the bar and the concrete. So, having an improvement also in the bond behavior. Another solution corresponds to the development of hybrid bar, for instance, using various type of fiber, or maybe using some steel bar coated with a layer of FRP, which can be made effective for reducing deformability and cracking, while still contributing to a pseudo-ductile behavior. And finally, of course, well, the use of some hybrid reinforcement, so the combination of both steel and FRP rebar, which can, if properly designed, both in terms of position and reinforcement ratio, can improve the strength and the deformability, as well as to guarantee higher durability. Then another key aspect that must be studied in further detail. It is related to the workability. That's why, because usually FRP rebar are mostly produced using some thermosetting resin, which once cured, they are brittle, so they basically cannot be shaped on site. So, and this can be a limitation in several cases. So the use of thermoplastic resin can help to overcome this issue, for instance, can allow the rebar to be shaped directly on site. But regarding this aspect, well, the mechanical characterization of this, I would say, new rebar are still ongoing. So further effort must be done by the scientific community regarding this topic. And finally, well, the aspect related to the durability. That's why, because, well, for sure, the influence of viscous effect occurring both in the concrete and the matrix of the composite can further the beam can get even worse. The serviceability behavior of the beam can get even worse due to this viscous effect. Regarding the rebar, well, I would say that the results that are available in the literature show that their mechanical behavior is not significantly affected by some of the more common environmental agents. However, well, the same is not for the concrete. So, although FRP rebar are characterized by high durability, concrete structure reinforced with FRP rebar may not be as durable. And finally, well, of course, there is the key issue regarding the behavior of FRP rebar when exposed to elevated temperature. That's why can be mainly associated to the organic nature of the FRP rebar, of the resin which compose the FRP bar. In fact, well, they present a glass transition temperature which usually varies between 60 to 100 degrees. So even for relatively low temperature, their mechanical behavior can be affected, and so the whole mechanical behavior of the beam of the reinforced concrete element can undergo some changes either in terms of failure mode or mechanical properties. In conclusion, the experimental results that were carried out, the experimental studies that were carried out shed the light on the fact that in general, the reinforced concrete beams presented a poor serviceability behavior, both in terms of cracking and deflection, as well as low ductility. In general, all the tested beams failed by crushing of the concrete, and it can be seen that their strength increased with the reinforcement ratio. The flexural stiffness of the tested beam at the cracking stage increased with the reinforcement ratio, while crack widths were decreasing with the reinforcement ratio. In general, regarding the analytical models, the model currently provided by the codes are able to provide relatively good estimates for both serviceability and ultimate condition. And finally, the analytical investigation that were carried out by the author highlights the fact that an accurate and reliable modeling is very needed to well predict the behavior of FRP reinforced concrete beams, accounting for the real constitutive law of the material as well as their interaction. So, thanks for your attention.